Okay, you're learning chemistry. Troy, greetings. We've begun. Leave them to fumble around. Don't let it annoy you that they're making dumb moves. Okay, you're gonna have to sit down.
I think this is gonna matter.
Okay, Via, you have to keep quiet, please. We're doing a lesson now. First of all, let's check. You guys okay with Lewis diagrams? Huh? More or less? No, not more or less. You okay or not? I'll tell you the things you need to do. There are certain things that I can't teach you. Now, it'll take too long. I can't teach you to do a Lewis diagram now. That'll take too long. I can teach you a Couper diagram from a Lewis diagram. That's very easy. So, if you consider that this is the Lewis diagram of H2O. It's the Lewis diagram. Very easy to turn into a Couper diagram, very easy to turn a Couper diagram into a Lewis diagram. You can go a bit back and forth between Couper and Lewis very easily. All you do is change the shared pair into a line, or back again. So, well, we could even do it right here. I'm going to turn this into a Couper diagram on the board. Take those two away, there you go. Take those two away, there you go. Okay, easy, right? Now it's a Couper diagram. Couper diagrams are useful for showing polarity of bonds. Okay, that's what these diagrams are good for doing. Of course, you need to know how to do a Lewis diagram, you need to know how to do a Couper diagram, this is how you change between them. Some other relevant examples of Couper diagrams. NH3, that's a Couper diagram of ammonia. By the way, these are all Couper diagrams. Okay, now this is NH3, this is H2O, and then another relevant example is CO2. Couper diagram, C dash dash O dash dash O. Okay?
Is this as complicated as
For Couper diagrams, yes. Because a line is a shared pair. One line is one shared pair. See now, yes, this is an example of, I can't really explain this to you now. You know, this is yeah. Look, let's turn this into a Lewis diagram in order to see. Okay, one line is one shared pair. That line is one shared pair. That line is one shared pair. That line is one shared pair. So the reason there's two lines is there's two shared pairs. Why are there two shared pairs? Because everybody needs 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Those are the 8 valence electrons for carbon. You're not supposed to draw that. Now we have the 8 valence electrons for oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Those are the 8 valence electrons for oxygen. So you see why it's like this. You need to have 2 shared pairs, otherwise not everyone is going to have a full valence pair.
So it's like the most complicated molecule we get in terms of your output.
So it makes sense how
Yeah. Okay, let's take it away. Most complicated molecule you have to draw in a Couper diagram. How about this one, methane? Just like this.
And then another one.
Is that it? Yes, we did lots of this stuff last year. Another example, CCl4. Cl. Carbon tetrachloride, yeah. Easy. See, I'm getting lazy sometimes. I've left off all of the valence electrons of chlorine. So each chlorine you see has 1, 2. It needs 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. Everybody needs 8. So you better get everybody 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's carbon tetrachloride. Another example. hydrogen, carbon. Oh, it should be a 3, sorry. What does this one look like? It's a C in the middle. H. Cl. 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 This is called chloroform, by the way. Heard of chloroform, that's called. Okay. What's the point of all of this stuff? The point of drawing Couper diagrams is to show the polarity of bonds. So let's use this as an example. Guys, please keep it down. Shh. Shh. Okay. Polarity of bonds. Polarity of bonds is very easy if you just listen to what you're told and you don't try to do your own thing.
So this is to do with the symmetrical.
Not
I
yet.
said,
Yes.
I want shaded.
Well done.
I'll be back in.
Yes. You beat shaded. Okay. Guys, please talk or whisper, talk more soft. I'm trying to give a lesson. Can't hear things. Polarity of bonds. Okay. Each bond has its own polarity. This bond has a polarity. That bond has a polarity. They're different. You don't add them, you don't multiply them. They've got nothing to do with each other. They're separate, okay? How do you work it out? You calculate this thing here. Yeah? Well, what is delta En for this? You work it out. It's the electronegativity of oxygen minus the electronegativity of hydrogen. And the same is true up here. You don't have to do the calculation again because you know the number is going to be the same. This will be equal to oxygen electronegativity. If you look over there on the periodic table, you see it's 3.5. So 3.5. Electronegativity of H is 2.1. Subtract them, you get 1.4. Now you know this also will be 1.4. Okay. Shh, guys, hey! No, sir. Can you all just be aware of your voices, please? You're talking loudly. Okay. You see it's the same. Because it's HO, HO. So we have the same delta E. You don't have to do it twice. What do you do now? On the diagram, if you are asked to represent this on the diagram, you need to use the following symbols. Delta plus and delta minus. That means a little bit positive. That means a little bit negative. This means a bit positive or negative. Cheers. Okay? Where do you put them? Well, you put it on the atom for each delta En. You put it on the atom that's more electronegative. So this bond here, which side is more electronegative? The oxygen. Right? So you put a delta minus there. And a delta plus here. See why? Because this is less electronegative. If it's less electronegative, that means it becomes slightly positive. This one is more electronegative, it becomes slightly negative. That's for this bond. You have to do it again for this bond. Okay? Yeah. Okay, cool.
So what's some dance?
Good luck, enjoy. Okay. We done, got it. Cool, right? So now we all understand polarity of bonds. It's pretty straightforward, that's how you calculate it, that's how you show it.
So it doesn't matter where you put it that delta.
No, just make sure it's at the end of the bond. Don't put it on the bond, that doesn't mean anything. Put it on the end. Okay. Cool. Okay, next. Now, we're done. Polarity of bonds. That's how it works. It's very easy. Well, I guess I should show you the table quickly, just for the sake of the video. The table of delta En and what you call everything. Delta En could be 0, right? It could be from 0 to 1. It could be from 1 to 1.8. or it could be greater than 1.8. These are the options.
So we did this in class today.
Yes.
So what is the WPC and SPC?
Weak polar covalent.
Strong here.
Yes. One type. Okay. Okay, so one type. If it's 0, it's non-polar covalent. If it's between 0 and 1, it's weak. Or you can say weakly or weak, doesn't matter. Weak or weakly polar covalent. Okay, and here, this one is strong polar covalent. Easy. And then this one, ionic. Super strong.
In what situation do you think
Okay. Now that's all you need to know about polarity. Okay, let's carry on. Now we're going to talk about shape. Let's talk about the shape of the molecule. Couper diagram does not show you the shape. The shape you must know by knowing some of the ideal shapes. Now there's, we go through the ideal shapes. There's a list of them. You can go look it up anywhere in the world. The textbook has the ideal shapes. I've drawn the ideal shapes on the board a few times. Your study guide has the ideal shapes. Your work schedule has the ideal shapes. Right? There's lots of ideal shapes. Okay, so let's go through some of the ideal shapes. The easiest one is linear. Okay, these are ideal. Easiest one is linear. It's just all the atoms connected in a line.
So what is that?
What are they for? They're just called ideal shapes. They're not for anything. It's a type of shape. They're the ideal shapes. What makes them ideal? I'll put in brackets here. When you get ideal shapes, you get ideal shapes when you have no lone pairs on central atom. Okay, so the atom at the center, they must have no lone pairs. Do you know what a lone pair is? Here's the diagram. Water again. That's a lone pair. You see? That is a lone pair. That is a lone pair. There are two lone pairs for water. That's a shared pair or a bonded pair. That's a shared pair or a bonded pair. So since there are no lone pairs in the central atom, that's linear. Easy. Ideal shape. Okay. Next ideal shape is called trigonal
As if something happens to you,
pyramidal.
agree to not take chances.
Yeah. Trigonal pyramidal. Sorry, I'm lying. It's not ideal. It's trigonal planar. That was a mistake. Trigonal planar is the ideal shape. What does it look like? It looks like a fidget spinner. Okay, it's in a plane. It goes like one atom, then atom, then atom, then atom. And if you looked at it from the side, it would look flat. So it's in a plane. That's why it's called planar, because it lies in a plane. When something lies in a plane, it means that from the side it looks flat. Okay. Next ideal shape is tetrahedral. Okay. What does that look like? It looks a lot like this one. But you see, you've got one atom coming out the front, so use a fat line to represent atom coming out the front. Then use a normal line to represent an atom in the plane of the board. Then use a dotted line to represent an atom down here, and then one line to represent an atom up there. Now, it's hard to show you, but maybe if I can do this. What looks like it. This, okay. Tough.
Why are they different lines?
Why are they different?
Lines is because of
Because the fat line means it's coming out the board, the dotted line means it's going into the board, the normal line means it's on the board. you must think in 3D now.
Yeah, so it's just the step. That's what the line is.
Huh?
The line is different to show that it's a step.
Yes. Okay, now. Okay, can you picture these three?
Oh yeah.
But now, imagine. Cheers. So you have three atoms on the bottom, one atom on top, but then you must take another atom and put it on top of that one. I can't get it to go very well, but you see what I'm trying to show you. There you go, it's coming. Something like that. In 3D. So you see one's in front, one's at the back, one's next to. Also, it's a bit more spread out than this. These bottom three, you must picture these bottom three are a bit more spread out. There's lots of pictures on the internet you can look at, tetrahedral shape, if you want to find out exactly, not this poor demonstration. Okay, why is it called tetrahedral? Because if you connect all of the exterior atoms are the ones that are not the central atoms. If you connect all the exterior atoms, you get a tetrahedron, which is a shape, a four-sided pyramid. You get one side, two sides, three sides, and then the front side is the fourth side. Okay, so let's just go back to this nice thing here. Okay. Tetrahedral. That's the ideal shape. Next ideal shape is called trigonal bipyramid. Okay. What is this one like? I'll show you what it's like. So, look here. Take this fidget spinner thing, okay? Fine with that? You just, hopefully you can imagine what I just did. Then I need a sharp object. Oh, here we go. Take that shape, right? And then you stick a pen through. See if I can do it. I'm sticking it through the middle, by the way. That's where I'm sticking it. Okay. Aha. So now there's the shape. It's like a fidget spinner with the pen through the middle. You've got an atom there, you've got an atom there. You've got an atom there. There's an atom in the middle. There's an atom here and an atom here. So in total it's 1, 2, 3 for these three, 4, 5, 6. So let's try to draw that. There's my flat, right? There's my flat bipyramidal fidget spinner. Then you've got one coming up, one coming down. That's my pen with the two, and you've got one in the middle. Central atom. Yeah. Cool. Pretty straightforward. And then the last one is octahedral. Octahedral is like this. And the x-axis. Let's do it like this. We've got 3 thermometers. It's good stuff. Just use whatever we can. Okay, there's, imagine that's the x-axis. Imagine that's the y-axis. Okay, can you imagine? Right. Here's the x-axis. Here's the y-axis. You're familiar with what I'm trying to show you? Cartesian plane. Here's the x-axis. There's the y-axis. Okay, now you do this. There is the new z-axis. It's at right angles. Every axis is at 90 degrees to every other axis except itself. Just making sense to you. X-axis, y-axis, z-axis. Yeah. Now imagine you just put an atom there, and there, and there, and there, and there, and there, and in the middle. That's the shape. Octahedral. Yeah. Easy. Now draw it over here. 1, 2, 3, 4, 5, 6, 7. Okay, easy enough. There you go, these are all the ideal shapes. Over here we need a list. These are all the ideal shapes. Now over here we need the non-ideal shapes. There's no proper word for this. It's not non-ideal, it's not a real word, but you know, the shapes that are not ideal. makes them non-ideal? What makes them non-ideal? Do you see these are the ideal shapes because they have no lone pairs. They're non-ideal because they do have lone pairs. So these are the ones that have lone pairs on a central atom. Okay, good times. Which are the ones you need to know? You only need to know two, I think. You need to know this one, which is called angular, by the way. Let me write angular here. That's an N. Angular. Okay. And the other one is trigonal pyramid. This one is like a tripod. Yeah. This is like a tripod, but with one sticking out the top. No, that's this one. It's like this one, but without one sticking at the top. So this is the same as the shape, but you cut the top off. So a fat line, normal line, dotted line, but you don't draw the top bit. So it's like tetrahedral, but you cut the top off. Let's try go now. Pyramidal. Shh. It's too loud. Okay. Okay. Got lots of shapes and stuff now. If you have the shape, oh, it's right. It's the music. If you have the shape and if you know the polarity of the bonds, you can work out